So I'm going to start the presentation. My name is Anton Antonov. I'm replacing Mitch Stonehocker. He was supposed to give the presentation here. I'll explain a little bit more about Christy Health. This is Mitch's company. Christy is his wife. She's chronically ill. Mitch is a former trader, a financial kind of guy. He has different financial companies. He started doing healthcare-related stuff because of his wife. And in some sense, he has a full-time job of taking care of the chronic conditions of his wife. I'm going to have 3 screens here. This is the presentation, this one. Here, we're going to see different websites, whatever. Christy Health is what is the company Mitch has. Yeah, and this is his wife with the chronic condition, as I mentioned. The other panel here, this is IntelliJ. I'll use it probably to explain some of the things I'm doing for certain things. But back to the presentation. All right. So the presentation, voice, grammar, compute, communicate. I did have somewhat different representation of the social contract, which is in this abstract written by Mitch. It is, I'm going to cover most of the topics he wants to talk about. I don't have much healthcare data. I'm going to use a substitute of the healthcare data. I'm going to explain that. So first, I assume people, at least to a point, are interested in conversational agents. And, you know, this is what we're trying to do. We're trying to do conversational agents for healthcare. There's certain market inefficiency right now, not certain, and huge, in American healthcare. This market inefficiency is basically almost everything. But one of the things is that hospitals, they don't share data, they don't share algorithms, everything is proprietary, they're very slow. Very often when people have certain conditions, being in a critical situation, in some sense, it's already a little bit too late. Maybe not too late, but if this was, caught earlier, the more adequate healthcare would have been given to those individuals. So the big idea of Christy Health is to be able to collect this data beforehand using mobile devices, using some other stuff. Now here we're trying to make a conversational agent that facilitates this kind of collection of data and management of chronic conditions. I'm going to show such a conversational agent design for management of diabetes. So, so this here, it's a simple breakdown of giving like some kind of a map of what's going on what we are trying to do. Right now, I personally design in this corner. I use finite state machines, and I use deterministic grammar rules most of the time. The deterministic grammar rules can be extended with stochastic rules. And those stochastic rules, they don't, I mean, you can continue that idea further and trying to stochastically derive grammar rules. That's not a trivial thing, though. The other axis here, it's the states in which we have the different. I do prefer the finite state machine perspective of designing conversational agents. So the finite state machines, they're basically like vending machines. You press D3, you put $5 or you put whatever some amount of money. If you have enough money, you get chocolate. If you don't, it doesn't give, it gives you just the money you put back. So you go for you can have different combinations, entering the money first, putting the code, and so forth. So finite state machines, this is one way to design conversational agents. This is what I do most of the time. In some sense, there's no way to escape this. Either people use it explicitly or implicitly. When people try to design conversational agents with stochastic methods, they're basically expecting with the lots of dialogues, with lots of text, the system to derive those states. Okay, I shouldn't be dwelling too much on this, but if you, so in this blog post, I have described, I think pretty well, the principles behind creating and programming domain-specific languages. One of the things I use a lot, it's called morphological analysis. And this is something we are going to see in the conversational agent. I'm going to represent, to show you here. This is on GitHub. I have a repository called Conversational Agents. In this conversational agents, there is a project Glucosa. And let's go to diagrams. So in this Glucosa diagrams, okay, so this is such a, this is the application of the so-called morphological analysis. In Glucosa, I'm not going to go through this, but basically, we're trying to find two orthogonal axes which describe the situation. We're trying to generate a grammar to make a conversational agent. Here you see the breakdown between the data types we're going to use for designing a diabetes conversational agent, like nutrition logs, like different databases for physical activities and so forth. And then we, on the vertical axis here, we have different type of functionalities. Obviously, we can, I mean, this can be extensive list. You can do a similar table, which I think it's probably here, which gives the breakdown of the different algorithms that can be used. All right, so with the domain-specific languages, I can actually show you, like, I mean, just to be a little bit more concrete, this should be live, I hope. All right, so what is happening here? I have this simple language, which is, you say, I like milk, I love milk, I want ice cream, whatever, right? And this language just gives you back certain. Well, I'm using Wolfram Alpha, and the internet connection is very slow. But you can see here, I hope you can see here how it does, it does actually, through the Wolfram Alpha call, it does give you the calories of the demands or whatever it is. So this conversational agent is just this. It just makes a statement about your food preferences, and it parses this abstract syntax trees you see here. And so basically, you can see how love food has been connected to love food calories here. And love food calories is basically, yeah, it's doing some computations here. I mean, you basically see how we're calling Wolfram Alpha and so forth. I mean, this probably won't finish, and I don't care at this point about it. But this is an example output from Wolfram Alpha. I mean, basically, I'm taking, in this particular implementation, just taking this this output and doing, and using it to make this response table, what was shown earlier. All right, so so Glucosa, I wouldn't. This was made for a different screen. The Glucosa was made as a competition entry for Alexa Diabetes Challenge, the Alexa Diabetes Challenge. And so this is organized by Amazon. We were not, my entry, or this entry was not accepted at the very beginning because I didn't discuss security. For some reason, security of the data and was very important for them, which, I mean, I understand, but whatever. Nevertheless, as I said, this is very well, in my opinion, documented and designed effort. And you can see different, I mean, like say this diagram, for example, is somewhere here, and you can see some other diagrams. If you go to this GitHub repository, there's some other diagrams showing different stages about Glucosa. So what is in this diagram? This particular design, it has two goals. It needs to serve individuals, like people who actually have the chronic condition. But it also can serve physicians who want to actually see statistics in general, like for a cohort of patients. Like everyone who has BMI above 29, and they're older than 35 and they live in Alabama or whatever. So that's why this color coding is doing that. So the green ones, they're more like on the physician side. They're basically using statistics on the whole set of patients who utilize this service. The ones here on the top, they're the core chronic condition management modules. The yellow ones, they're more like motivational, like you want to banter with some other diabetic people how much you lost, like how many pounds you lost, for example, or whatever, if you feel competitive. There's some kind of social networking element. So there are several elements in this. What is happening here? I mean, it's here you see, this is in the background, but it's basically, these are the different grammars, the different finite state machines and etc., which are being designed behind the scene. All right, so actually, I would like to show you a possible grammar here, which was in the. I was unable to download this from Google, but for example, maybe we should look at this PDF. I mean, you can see there are different onboarding grammars and etc. And so there are different rules, like these grammars, they allow you to say, my name is this, and I'm 29 years old, and I'm diabetic, and so forth. And actually, I think I have a better PDF here about this. Like this design document, there's an example here. Like, so this is the onboarding module in which we proclaim different parameters of the user. Then we do certain, then we're supposed to be able to query, to be able to handle this kind of queries. And to provide certain explanations and so forth. Okay, here you can see some kind of statistics. This is from the physician perspective to kind of see statistics of a population of people. I'm not sure how important is this. I think more important is to discuss this next diagram, which again, apparently I should zoom out from it. So how will you see this? Okay, thank you. This is an important, this diagram shows an important methodology, which I already kind of illustrated here in this particular example with the food. So you see, this is this here, it's a Bacchus-Noor code. This is a human readable code. From this Bacchus-Noor code, I generate parsers. If we look at the output here, these are parsed. Like for example, this one was turned into this parser. This is actually code generated from this particular, formalism for explaining grammars. After this is done, so back to this picture here. So we do gather specifications and etc. We do some parsing experiments. After we have figured out what kind of grammars we want to implement, then we generate the grammars. This is a very powerful technique. I have implemented this generation of, we generate the parsers from the grammars. I have implemented it in several languages. Mathematica is the best for this. There's some possibility to modify the parsers and to do some other stuff. Here, what we supplement this activity is, for example, we can enhance it with different studies like entity name recognition and etc. Using some different modules like spell check and entity name recognition, you can improve your parsing abilities. Let me show. So because this is one of the things we are trying to do, and if you have been in my previous talk, it's somewhat related to this. I'm using here wine data as a representative of vitals of vital signs time series. And these distributions you see here, although they're for wine type of chemicals or whatever, they're very similar to the distributions you'll see about, say, heart rate and respiratory rate and so forth. So this classification pipeline, we actually have a way. This is a domain-specific language programming domain-specific language, and we have a way with grammars and parsers to map into this in this particular pipelines. My previous talk, if you haven't seen it, my previous talk in this conference was describing that. What is important here from Christy's Health perspective and what we are kind of pushing is that we actually do have this decision thresholds. Like this is very important. You need to receive operating characteristics. They come from the Second World War when you have a radar and trying to figure out an airplane. Is this airplane yours or enemy airplane? So how much you want to have an enemy airplane at the back of your army? How much you want to shoot your own plane? So similarly here, how much you want to leave someone who is with critical condition to die? How much you don't? So if you have like two teams or 3 teams of physicians and nurses, obviously it's you can spread them out and they can monitor different people. If you have one team and the hospital ward is basically 2 different buildings, how do you schedule where they go? You need to be able to make a selection. This is happening in this way. One of the things I really like about this, we use quantile regression. Granted, quantile regression, I mean, it's just the better way of doing time series analysis. So in this particular case, what I want to show is that I'm actually generating some random pipelines here. You can see if I generate, so I have a quantile regression solution, this here, this is a quantile regression, you see the pipeline here. Imagine that I have randomly have put this kind of, I can randomly select this kind of elements. This is what is happening here, this is what I'm showing you, and if I generate this again, we will see different pipelines. Also, let me run this. This is basically, so I'm making a bunch of random tests, and then I'm running them. This is one way for me to catch mistakes. It's extremely important with this pipelining, like what we saw the pipelines here for. This is not quantile regression, this is the classification, but it's exactly the same principle. It's extremely important when you map natural language into this kind of pipelines to be able to fail gracefully, or you need to design for failure. So that's why I'm testing this in this way. The finite state machines, well, this is basically a general diagram. We're using Mathematica, but ultimately we want to get out of Mathematica. I mean, if we want to go in production, I mean, both Mitch and I, we're pretty good with Mathematica, love it. But ultimately, at some point, we need to consider getting out of Mathematica and using some of the production level libraries. So it's very important for me to be able to use the libraries I have listed there, Spark and H2O. H2O is written in Java. Spark is written in Scala, but it's a Java virtual machine type of thing. And you can see, I mean, we're basically addressing this. We have grammars and conversational agents that let you load the data, transform the data, make the classifiers, test different metrics, and display them. We are reading, medical records data. The patients and demographic data is just conditionally separated here. We also have a design which lets us encapsulate the transformations in a particular way. This is the finite state machine I was talking about. So we're waiting for a command. If the command is load the data, we get the data. Now, again, if the command is load data, we go into the state data loaded and so forth. So I'm using this kind of state machines finite state machines to design the dialogues in the conversational agents. What you saw maybe in one of the talks with Wolfram Alpha, when they're saying, okay, differentiate that, they meant the last state. It's something like this. In some sense, this is more comprehensive because I actually always know what was the last command, and I actually can figure out, I can retrace my steps at any point. All right, so this was it, and thank you for your attention. Please, yes. Yeah. The what? It's Mathematica. Yeah, Mathematica, but it doesn't matter. It's more a conceptual device, right? I mean, I use Mathematica. If you look at this, I mean, I need to probably, I guess, accentuate this more. But if you look at, say, where was it? Conversational agents. But all right, I do have in my GitHub repository, for example, here, there's this is connected to GitHub, right? I mean, if we do this conversational agent, I mean, it's fairly well described. There's also a YouTube movie doing stuff with it. I mean, it's showing different how different functionalities are implemented. If you want to figure out how to use these finite state machines in Mathematica, it's one way to do it. Right, my grammars, they do, in some sense, the grammars themselves, they have finite state machine behind them. But this is a more on a more macro level. So as I said, like for example, for this phone book type of diagrams, you can see, like for example, if you get a query, I want to talk to an engineer from what company, what is the name, and so you go through this kind of states. There is this waiting for a filter. You filter your queries. You get only one person, and then you can dial. You can make a dial to the phone, or you can just press with a button on a list which is being returned. But these are the finite states I'm going through. I can use voice to command this. I can use also some other ways to interact. What I'm going to do here, it's I'm going to open a diagram which I think is going to explain this well. And so let's see, patient conditions prediction framework. Somewhere here. Just a moment. I need to browse through this. Yeah, there's a. Okay, unfortunately, this is not very good, but this is a. Okay, I'm going to open it. This is a continuous testing cycle. So this is like, imagine you want to do DevOps, if you know the term, I assume. You want to do DevOps for data science. And you want to do DevOps for machine learning algorithms for healthcare, or whatever, right? If I have changes in my data, I want to be able to run this new data with the old classifiers I have and see what are the results. I also want to retrain a new classifier with this data and see what results I'm going to have, and so forth. This cycle here, I'm going to be storing both the data and the models and the classifiers I'm doing. Like if you use Java, you can always download the so-called plain Java object. So you can have a database of the models you are producing every day with different data and so forth. And you can actually see when somebody say, if you have a database, you use Mathematica. Wow, there's a new speaker. Okay, yeah, sorry. Okay, yeah, we can use Mathematica and analyze what happened with this person who broke the whole thing. Thank you.